Boom. All right, ladies and gentlemen, welcome. This is the voice of Dr. Julie Ben. Yeah, Quintessence Tutorials, aka Julie Ben Schools as well. Okay, so I'm going to be your presenter in this video, and in this video, we are going to be discussing Chem 101. Oh, first, let me introduce myself properly. Julie Ben, Dr. Julie Ben, PhD in Electrical Electronics Technology, and I will be very much in charge of Chem 101. Okay, so Chem 101 happens to be a very broad topic. Trust me, very, very broad. Okay, it is, in fact, if there is a word like broadest, it is the broadest topic you will see in the whole of your 100 level. Okay, before now, Chem 101 was called Chem 111, and it was just 6 chapters for first semester, while second semester another 6 chapters. Okay, so but now as we speak, it has been amalgamated as one, and you are offering a total of 12 chapters in Chem 101, and that means you're doing the job of 2 semesters put together as one. Welcome to University of Benin. Okay, Uniben is a very interesting area. So let me list out the 12 topics you're going to be seeing in this chapter, but this video will be purely designed for chapter 1. Okay, so first, chapter 1 is atoms and molecules. Chapter 2 is the laws of chemical combination and quantum number and configuration. Chapter 3 is stoichiometry. Oh yes, the longest part of it all. That has a lot of questions. Stoichiometry, calculations in chemistry. If you have calculation issues in chemistry, don't miss any of my videos. Don't miss any of my live classes at Quintessence Tutorials. Then chapter 4 is hybridization. Yeah, the almighty hybridization, full of shortcuts. Okay. Then you also have the next day, which is radioactivity. Chapter 5 is redox reaction. Okay, redox reaction. Then chapter 6 is states of matter. Chapter 7 is periodic table. Chapter 8 is acid, bases, and salts, aka ABS. Chapter 9 is acid-base reaction, also called AB reaction. Chapter 10 is colligative properties. Chapter 11, chemical equilibrium. And chapter 12, nuclear chemistry. So you have to study all these chapters put together just for this course of Chem 101, and the credit load is just 2 credit loads. Too much work for just 2 credit loads. All right, let's get started. Boom. Atomic theory, the history of an atom. Let's start with history of an atom. Now, the atom actually has no date of when it was discovered, but from records from the 15th century, a great philosopher, the person of Democritus, defined matter as being made up of very indivisible particles, which he called atomos. Although his idea was rejected by some philosophers, we talk about Plato and Aristotle as the case may be. But according to Aristotle, matter is actually made up of a very tiny particle called atoms. Now, no, I actually mean that according to Aristotle, matter is not made up of tiny particles called atoms, just like Democritus said. So according to him, matter is made up of 5 basic elements, which he named ether, water, fire, air, and the earth. Although he was very wrong in his definition, but this definition of his stood for over 2,000 years based on how eloquent he was and, was able to convince a lot of people. Aristotle was very influential in his time. Ether actually is the outer surface of the earth. That's what ether means. Now, but according to Plato, matter is divisible into smaller and smaller pieces without limit. That means you cannot finish matter. You will divide and divide and divide and divide and divide and divide. It will not have any limits. That is Plato's definition of matter. Now, his teaching actually continued over the years until the coming of John Dalton in 1808. John Dalton made some hypothetical statements about matter, about 4 of them, which actually stood the test of time till today. And the first of them said that matter is made up of small indivisible particles called atoms. He went further to say that these atoms can neither be created nor be destroyed, and he also said that atoms of the same elements are identical but completely different from atoms of other elements. And then the last part of his postulation was that the chemical combination of atoms takes place in whole number ratios. Now, this is exactly what John Dalton postulated in 1808. But over the time, scientists got to discover that all these theories hypothesized by John Dalton actually had commas. Commas in the sense that they were actually discovered that the atoms were divisible. Instead of the word indivisible, they were found to be divided into proton, neutron, and electrons, and even further divisible into quarks, And then also, he said atoms are neither created nor be destroyed. Exothermic reactions destroy atoms. And then atoms of the same elements are identical but completely different from atoms of other elements. Isotopes. Formation of isotopes is a contradiction to that. And then he said chemical combination of atoms takes place in whole number ratios. Polymerization reaction. They occur not just in simple whole number ratio, but in terribly wide range of numbers. All right, so basically that is that. Let's go straight to the atomic structure. Now, based on John Dalton's definition of an atom, one can actually conclude that atoms are the basic unit of elements that can partake in a chemical reaction. Basic unit of element, that is the word. Basic unit of elements that can partake in a chemical reaction, not indivisible, as the case may be. It was later discovered that protons and neutrons and electrons are subsets of an atom, which we are going to see one after the other. So we kick off with the very first part there, which is actually the discovery of the electron. Now, the discovery of the electron was championed by J.J. Thomson. J.J. Thomson, that bunk on J.J. Thomson. He actually made use of a cathode ray experiment. The cathode ray experiment wasn't discovered by him. It was discovered by Williams Crook. The cathode ray experiment consists of a vacuum tube with two terminals, positive and negative. The positive terminal is to the anode, the negative terminal is to the cathode, and then it has a pump evacuator that is used to remove air inside the cylinder, to evacuate air from it to make it a vacuum. And then these two positive and negative terminals are connected to a very high voltage supply of about 6,000 volts. Now, this is what a vacuum, or let me call it a cathode ray experimental tube design looks like. So J.J. Thomson capitalized on it and studied this ray. As soon as high voltage was passed by J.J. Thomson, he discovered that rays were actually moving from the negative plate to the positive plate. And these rays that were moving from the negative plate to the positive plate, he studied them one after the other and came up with the following conclusions. The very first one, he says that cathode ray travels in a straight line. That is to say that these rays actually move in a straight line. And then he also went further to say that they are made up of particles that produces mechanical motion. They have the power to penetrate metallic foils. They reflect both in electrical and in magnetic field. In an electrical field, they deflect towards the positive terminal because they are electrons, while in a magnetic field, they deflect towards the north pole because they are electrons. And then also, due to this behavior, J.J. Thomson decided to call this ray an electron. And of course, when he named it an electron, the charge was the next thing to be discovered. And the charge was discovered by Millikan, R.A. Millikan, in his oil drop experiment, through one of the formulas postulated by J.J. Thomson, which is the charge per mass of an electron. So the next on the discovery line is the X-ray. Now, the X-ray was further research work was done on the cathode ray experiment. Further research work was done. Now, Williams Roentgen still researched on the cathode ray experiment and came up with an X-ray discovery. Now, how did this happen? He just started by striking the cathode rays that were coming out from the negative terminal in a vacuum tube. He has to strike them on a glass and a metal sheet. And as soon as he was able to strike this ray on a glass and metal sheet, he discovered a very energetic ray that was produced that could penetrate through matter, that could darken covered photographic plates, that produces fluorescence in various substances, and most importantly, that do not have deflection in both electric and magnetic field. So he was a little bit perplexed. We're talking about Roentgen now. Williams Roentgen was quite perplexed, and because of that perplexion, he decided to call it X-ray, or simply put, highly energetic ray. So that is how X-ray actually was discovered. Although there is another way X-ray can be discovered through the K capture, but this is actually fundamental. Now, not quite long after Roentgen discovery, the X-ray, not quite long after Roentgen discovered the X-ray, Antoine Becquerel accidentally found that radioactivity. How did he do that? He actually isolated uranium particle on his way probably to lecture, and then put it in a foil and discovered that it had almost the same physical properties with X-ray. It's able to darken photographic film. It is able to penetrate through substances. And he has discovered that they emit radiations over the time. So this is actually what Antoine Becquerel's discovery was all about. Antoine Becquerel. So these radioactive substances emit alpha, beta, and gamma rays. This was discovered by Rutherford. Okay. So, however, Marie Curie, that happens to be his PhD student, she was just a student under Antoine Becquerel. So she actually isolated some other elements, polonium, radium, and she noticed that they also exhibited the same kind of properties. She named it polonium because she was born in Poland, so she decided to name it after her place of birth, polonium. So the thing there is that after she was able to isolate this amount of elements related to that of his master, that's Antoine Becquerel, she suggested the name radioactivity to be given to them. Let's call these substances that emit radiation on their own, that emit radiation spontaneously, let's call them radioactive substances. And that is how the study of radioactivity came into play, by just an accidental discovery. Now, it is important to note that these particles emitted from radioactive substances are done spontaneously. Spontaneously in the sense that nothing actually brings about nothing prompts the emission of these particles. These particles are emitted on their own. Pressure has no effect in the emission of the particles. Temperature has no effect. Chemical reaction or chemical change also has no effect. And it's important for you to also note that no radioactive substance, I repeat, no radioactive substance has the power, has the effrontery, has the temerity to emit all three particles at the same time. The maximum a radioactive substance can emit is 2. Either you emit alpha, beta, or beta, gamma, or any one. The maximum is 2. Uranium, for example, can emit alpha and beta particles simultaneously. Okay. Now, properties of an alpha particle. Alpha particles have a helium nuclei. They are positively charged. They have a mass of 4, and they have the lowest speed because of how heavy they are. They, however, have the highest penetrating. No, they can have the highest penetrating power. They slightly deflect in the presence of a magnetic and electric field. They have the strongest ionization power because of how heavy their mass is. Now, this is very important. They have the highest ionization power. Ionization power is dependent on the mass of the substance, okay? So alpha particle happens to be the heaviest of all three particles, hence has the highest ionization potential. And then also, it has the ability to act as a charge carrier in semiconductors. That's alpha particles. So that takes us to beta particles. Beta particles are electrons. They are negatively charged. They has a mass of 1/1840. And then they actually have a high speed of penetration. Their speed is higher than that of alpha particle. They can be stopped by metal foils, while alpha particles can be stopped by thick paper. They have a greater deflection in both electric and magnetic fields. As far as alpha particles are concerned, just a slight deflection. And then when it comes to ionization power, they have a weaker ionization power compared to alpha particle. Then we're still talking about beta particle, and of course they don't act as charge carriers in semiconductor. In fact, they don't have any effect. So that takes us to gamma particle. Gamma particle actually is electromagnetic wave, not a particle. So gamma is not a particle, it's actually a magnetic wave. So I call it gamma particle, it's not a particle. Pardon me for that. Now they have no charge, they experience no deflection in both electric and magnetic field. However, they have the highest speed. They have the highest speed, yes, equivalent to that of light, and also have the highest penetrating power. They have the highest speed, they have the highest penetrating power, but as far as ionization energy is concerned, ionization potential, they have the lowest ionization potential. Very, very important. Take good note of that. So that takes us to Rutherford's discovery. Now, just as a brief statement, Rutherford actually is known to discover, number 1, the nucleus of an atom, and then number 2, the proton. Now, the nucleus of an atom actually was discovered from his scattered ray experiment. I will explain what the scattered ray experiment is all about. Now, according to Rutherford, he carried out an experiment on radioactive substances. He didn't make use of cathode ray, just like the trending cathode ray in his time. He decided to go into radioactive substances and then carried out an experiment using foil goals and other methods and discovered that most particles penetrate through the foil with slight deviation, while others will penetrate through the foil without even deflection at all. Now, those ones that penetrate through the foil with a very slight deflection, he named them beta particles. Those that do not deviate at all through the foil, metallic foil, those ones are the gamma rays, right? Or the gamma wave, as the case may be. Now, as if that was not enough, he also discovered that some particles actually experience a very wide deflection in a metallic foil, and at times discovered that it takes a 360 degrees return from its position. This experiment is referred to as the angle scattering experiment. The simple reason is that the angle at which these rays are being scattered tends to be wider in alpha particles. And he now said, this aluminum foil has an atom. Inside that atom, there is a nucleus. And inside that nucleus, for an alpha particle to experience a 360 degrees return simply means that there is a particle inside that nucleus that is positively charged. And that particle that is positively charged, he decided to call it proton. Proton, because it will only take a positively charged particle to be able to have a 360 degrees return of an alpha particle which is known to be positively charged. And that is how he discovered that. So according to Rutherford as well, he also defined an atom as comprising of a central nucleus surrounded by clouds of electrons. And he said the size of the nucleus compared to the size of an atom is 1 all over 10 raised to the power 13, the size of an atom. That was his discovery. That was his definition. Although J.J. Thomson wasn't too happy with it, because according to J.J. Thomson, an atom is made up of a sphere with scattered electrons and protons inside, like plum pudding. So it is called the plum pudding model, J.J. Thomson. So he wasn't too satisfied with that, but who cares? That is his business. Millikan, R.A. Millikan, he's known to be a charge tester. Having discovered the proton, J.J. Thomson discovered the electron, Rutherford discovered the proton. Millikan just came to test the charge as usual, and of course ascertained that the charge is the same as the charge of an electron, just that it is now having a different sign. The charge of an electron is negative, the charge of a proton is positive. The magnitude of the charge in an electron is 1.6 times 10 raised to the power minus 19 coulomb. The magnitude of the charge in a proton is exactly 1.6 times 10 raised to the power minus 19 coulomb as well, but just different in sizes. However, the game was not over. Rutherford, in his experiment, there was a little puzzle, that came up some time ago. A little puzzle came up. Despite the discovery, there was still a little puzzle. And the puzzle was between hydrogen and helium. Hydrogen is known to have 1 proton, 1 electron, and therefore has a mass of 1. A helium particle has 2 protons and 2 electrons, but the mass of a helium particle is 4. So the big question is, what brings about the extra 2 in the weight of a neutron particle? Because a helium particle actually is supposed to be 2 and not 4. So where is the extra mass coming from? So Rutherford and his co-workers, plunged into serious academic research, trying to find out what brought about the extra mass in a helium particle. And then unfortunately for him, he was not able to discover that before the almighty Chadwick, in his experiment in 1932, revealed that particle. And how did he do that? He bombarded beryllium with an alpha particle. The alpha particle was coming from polonium. Polonium emits alpha particle and at times can even emit beta. So the alpha particle emitted by polonium, he struck it on a beryllium particle, and a mysterious particle, very energetic, was released. This mysterious particle does not deflect in the presence of a magnetic or an electric field. This mysterious particle happens to be heavier than the proton. This mysterious particle happened to have no charge because R.A. Millikan came to test for the charge of the particle, and there was no charge, So this particle was so mysterious that Chadwick had no choice than to name it neutron. Why? Simply because since you are neutral to both electric deviation and magnetic deviation, since you are neutral in terms of charges, and you even happen to be heavier than the heaviest known particle of an atom then, which was the proton, he decided to call it neutron. And that solved the puzzle between hydrogen and helium. Very, very important. And the weight of this neutron particle was known to be 1.67495 times 10 raised to the power minus 24 grams. If you want it to be in kilogram, it's minus 27 kilogram. So all in all, J.J. Thomson found that the electron, Millikan tested for the charge of the proton and the electron, Williams-Roentgen X-ray, Maria Curie suggested radioactivity, Antoine Becquerel actually is radioactivity founder, Rutherford through his scattering experiment found that the proton and the nucleus as well. And then Chadwick was known for the neutron. Very, very important. So the next thing we are going to look at are the different relationships in an atom. We start with the atomic number. Atomic number is simply the number of protons, found in the nucleus of an atom of an element. That is the atomic number. For a neutral atom, atomic number equals proton number equals electron number, okay? Next is the atomic mass. Atomic mass is simply the sum of the protons and the neutrons found in an atom, except in hydrogen that has no neutron, okay? So then, when you talk about mass number, you talk about the algebraic sum of the proton and the neutron. And then that takes us to isotopy. Isotopy simply means atoms existing with the same atoms of the same atomic number but different mass numbers. For example, isotopes of hydrogen, proton, deuterium, tritium, as the case may be. Now the next thing we are going to talk about is isotons. Isotons are known to have the same neutron number. A typical example of isotons are carbon and nitrogen. Carbon 14 and nitrogen 15 are referred to as isotons. Then isobars have the same mass number but different atomic numbers. Example is potassium 40 and calcium 40. Then you have isoelectronics, which have the same number of electrons. For example, oxygen 2- and neon. They are referred to as isotons. Then there is another one we call isodiaphers. Isodiaphers are known to have difference. They have same difference in neutron and proton numbers. Take note, same difference in neutrons and proton numbers. That means by the time you find a difference between the neutron and the proton number in an atom, the answer you get, if it happens to be the same with the difference in neutron and proton of another atom, you refer to them as isodiaphers. For example, fluorine and sodium. These are typical examples. Other examples are uranium-92 and thorium-90. They are referred to as isodiaphers. Uranium-92 has a mass of 238, while thorium is 234. By the time you get the proton number and the neutron number and find the difference between the two, you will have the same figure. So the next thing there is the atomic mass unit, AMU. Atomic mass unit, one atomic mass unit is defined as a mass that is exactly equal to 1/12 the mass of carbon-12. The mass that is equivalent to 1/12 the mass of carbon-12. Now, carbon is used as a standard because carbon is the only element in the periodic table that is known to have equal number of proton, neutron, and electron. 6 proton, 6 electron, and 6 neutron. That is why it is used as a standard. So 1 AMU is simply the mass of one carbon-12 atom divided by 12. That gives you one atomic mass unit, okay? So that takes us to average atomic mass, aka average or average abundance, as the case may be. So for you to calculate the average abundance or the relative abundance of a particular compound, all you need to do is to find the product of the percentage abundance times its AMU. The algebraic sum of the percentage abundance and its AMU will give you the average atomic mass of that substance. Okay, so for example, carbon is known to have carbon is known to be an isotope of 2 elements, which is carbon-13, carbon-12, for example. Carbon-13 has 1.11% abundance and has an atomic mass of 13.00355. And then carbon-12 has a percentage abundance of 98.85% and has an atomic mass unit of 12. So all I need to do is to multiply 1.11 all over 100 times 13.00335. That gives me for the first isotope. Then I will add it to the second isotope, which is carbon-12, which is 98.89 divided by 100 times 12 atomic mass unit. Then I will add the two together. Any value I have will give me what we call the average atomic mass of that substance. So molar mass, of course, simply stands for 1 mole of a substance contains as many elementary entities, as many particles as in exactly 12 grams of carbon-12. It is important for you to know that 1 mole of a substance weighs 6.02 times 10 raised to the power 23 particles, and that is Avogadro's number. 1 AMU is equivalent to 1.661 times 10 raised to the power minus 24 grams. 1 gram of a substance is equivalent to 6.02 times 10 raised to the power 23 atomic mass unit. That is to say, 1 mole of hydrogen contains 6.02 times 10 raised to the power 23 atoms of hydrogen. 1 mole or mole is simply given mass all over molar mass. Then the last thing we are going to see is actually empirical formula and molecular formula. Empirical formula actually is a formula that gives you the simplest whole number ratio of the constituent elements in a particular compound. For example, benzene is C6H6, so it will give you the simplest constituent. So there is only carbon and hydrogen. That gives you what we call empirical formula. But as for molecular formula will go a long way to show the actual number of the different elements present in that molecule or that compound. So benzene is actually 6 atoms of carbon and 6 atoms of hydrogen. So all of them will surface in that formula. So that's the difference between the two. Now, how do you calculate empirical formula? For you to calculate the empirical formula of a given compound, first you have to be given their percentage abundance, right? So once they give you the percentage abundance, just divide them by their atomic masses. Once you divide each of them by the atomic masses, the values you have, you pick the smallest value and divide everything with it. And by the time you do that, you are going to have whole numbers. Those whole numbers signifies the constituent elements, okay? Now take note. At times you may end up having 0.5, at times 0.3. You have to multiply by either 2 or 3 so as to have it in whole numbers, okay? Then as for the molecular formula, all you need to do is to just put in bracket your empirical formula with N as a subscript, then equate it to the relative molecular mass. Okay, and once you do that, make N the subject of the formula. Whatsoever N gives you, substitute it back in the empirical formula with a bracket of N. Open the bracket by the N value you have gotten, and then boom, you have the molecular formula with you. However, there are shortcuts to calculating empirical formulas, especially when the molecular mass is given. If the molecular mass of a substance is given, all you need to do is just to pick the options and start calculating for their relative molecular mass. Which of them is going to give you the same relative molecular mass as it is given to you in the question? Once you are able to pinpoint that, be rest assured that that is the correct empirical formula or the correct molecular formula of that particular substance. So thank you very much. This is what chapter 1 is all about, and I think we have done justice to this chapter. It's a little bit longer. It's about 26 minutes, but then it's worth it. If you can spend 26 minutes to listen to this tape, I'm sure you will gather a lot. Thank you. God bless you. See you in chapter 2. Boom.